Good afternoon, class and Miss Roy. Today I'm going to be talking to you about magnets in particle accelerators. But before I begin, I want to briefly cover what exactly I'll be discussing in this presentation. First, I'll begin with a description of the device in question and relate that to the principle of superconductivity. Then I'll discuss the principle of superconductivity in depth, with an emphasis on the underlying physics behind the superconductors used as particle accelerator magnets. I'll be directing your attention to a couple of diagrams throughout both these segments of the presentation. Finally, I'll briefly cover all advantages of using superconductors in particle accelerators, but that isn't where the fun ends. To make sure all of you don't drift off, I will ask a question directly relating to a topic in this presentation. So, what are particle accelerators? Particle accelerators are machines designed to accelerate fundamental particles to high energy states by producing beams of charged particles. These beams are then studied by researchers for advancing fields of industry such as computer chip manufacturing, medicine through the development of various types of cancer therapies, and security such as material characterization, in addition to discovery science. The particle vector desired dictates the strength and direction of both the applied electric field, which controls the particle's speed and beam energy, and magnetic field, which steers and focuses the beam. The right-hand palm rule is also used to determine the direction of the beam. The principle of superconductivity allows for certain materials called superconductors to reach zero electrical resistance and expulsion in magnetic flux fields, which is only achieved at extreme cool temperatures, often near absolute zero, where electrical resistance is proportional to temperature. Key components mentioned in this diagram of the Large Hadron Collider cryodipole are superconducting coils, vacuum vessel, and cryostat, which hasn't been labeled. The vacuum vessel allows for a beam of particles, electrons, to form. The superconducting coils enable for these particles to reach great speeds, and the cryostat allows for the superconducting coils to do this by reducing its temperature to the extreme cool temperatures required for the superconductor to function. Superconductors have commonly been used in particle accelerators since the 1980s. There are two kinds of superconductors, Type 1 and Type 2. Modern particle accelerators use Type 2 superconductors. The exact mechanism for Type 2 superconductors is currently unknown, but it has been theorized that it is related to magnetic interactions. When selecting a superconductor for a particle accelerator, both engineers and physicists actively work to minimize the effect of vortex state and flux pinning, as it is undesirable because they lead to hysteric losses in alternating magnetic fields, reducing the overall efficiency and capability of the superconductor and, by extension, particle accelerator. This diagram shows a graphical comparison of the effect of an applied magnetic field and magnetization between Type 1 and Type 2 superconductors. Type 2 superconductors will keep out the whole magnetic field until the first of the two critical fields have been reached. Upon reaching the first critical field, shown as Hc1, a magnetic flux quantum penetrates the superconductor, called vortices, which trigger the circulation of current. But due to imperfections in a superconductor's crystal lattice structure, a crystal boundary forms which prompts flux pinning and vortex motion is stopped. The superconductor is still in its superconductive state at this point, but only until the second critical field, Hc2, has been reached. Hence, Type 2 superconductors can sustain their superconductivity until Hc2 has been reached, superseding Type 1 superconductors in magnitude, as shown in the diagram. The use of superconducting magnets in particle accelerators is greatly advantageous to particle accelerator technologies because they enable greater speeds for charged particles to achieve, allowing for a higher number of scientific breakthroughs in industry, medicine, security, and discovery science, in addition to reducing the overall cost of particle accelerator operation relative to the use of non-superconducting magnets. Modern particle accelerators such as the Hadron Collider could not be built without the superconducting materials and technologies. Now it's that time of the presentation where I will ask a question based on one of the topics covered, and after I do, you will have 3 seconds to come up with an answer before I call time's up, and ask which option each of you chose, ranging from A through to D. If I call out an answer you believe to be right, put up your hand. What is an example of an industrial application of a particle accelerator? Time's up. Who thinks the correct answer is A, discovery science, or B, computer chip manufacturing, or C, material characterization, or D, cancer therapy? The correct answer is B. Thank you for listening to my speech. I hope you found it enjoyable.